Let's take a look at the atomic bomb first. Those who have made an atomic bomb know that the principle of the atomic bomb is actually not complicated. Why is it that something that appears in middle school textbooks can still only be manufactured by a few countries? The main material for making atomic bombs is uranium. The atomic number of the element uranium is 92, and it mainly exists in nature in the forms of uranium-235 and uranium-238. Uranium-235 contains 92 protons and 143 neutrons, while uranium-238 contains 92 protons and 146 neutrons. This type of element, with the same number of protons but different numbers of neutrons, is also called an isotope. Compared to uranium-238, uranium-235 is very physically active, making it a suitable raw material for making nuclear bombs. However, in nature, 99.2% of uranium exists in the form of uranium-238, while uranium-235 accounts for only 0.7%. If uranium-235 is enriched to about 4%, then it is low-enriched uranium. If enriched to about 90%, it is high-enriched uranium. Low-enriched uranium is used for building nuclear power plants, while high-enriched uranium is used for making nuclear weapons. Here's a question: this high-enriched uranium looks quite ordinary, so why can it unleash such earth-shattering power? This brings us to nuclear fission. When a neutron is used to bombard a uranium atom, the uranium atom splits into two smaller nuclei, simultaneously releasing 2 to 3 neutrons. Scientists have calculated that during the fission process, the mass of the atom actually decreases. Where did the lost mass go? According to Einstein's mass-energy equation, mass can be converted into energy, and energy can also be converted into mass. Therefore, the lost mass is ultimately converted into energy. The new neutrons produced by fission will collide with other uranium atoms, continuing the fission reaction, thus forming a fission chain reaction. This fission chain reaction will continue, eventually unleashing a cataclysmic amount of energy. There are mainly two types of atomic bomb designs, one being the gun-type design represented by the little boy atomic bomb. Another type is the implosion design represented by the Fat Man atomic bomb. Let's first look at the gun-type design of Little Boy. If we take it apart, we will find several rings installed at the front and back, and these rings are made of highly enriched uranium.
The uranium ring of the warhead is approximately 25.4 kilograms, and the uranium ring of the tail is 38.5 kilograms. At the tail of the atomic bomb, there is an electronic detonator, which is the ignition device of the atomic bomb, connected to the smokeless explosive nearby.
Next is the steel shell, mainly used to encase the nuclear fuel and detonation device. Above is the pressure sensor hole, used to connect to the pressure device. In the middle, there is a long gun. The uranium rings mentioned earlier are installed inside the barrel. This is a sensor that can trigger the ignition device upon receiving a signal. These are safety pins to prevent the atomic bomb from exploding during transport. This is a tungsten carbide steel casing, mainly used to control the critical state of the nuclear reaction. In front is the tungsten carbide plug, which has some neutron initiators installed on it to ensure the chain reaction starts properly. This device is a radar altimeter, which can accurately measure the detonation height. Atomic bombs are generally delivered by aircraft. Before the atomic bomb is dropped, the safety pins on it will be removed. 15 seconds after the bomb is dropped, the air pressure sensor will be activated to determine the approximate altitude of the bomb. When it descends to the predetermined altitude, the radar altimeter on the casing will be activated. When the radar altimeter detects that the atomic bomb is only 580 meters from the ground, the electronic detonator is activated, igniting the smokeless explosive nearby. The thrust from the explosive will propel the uranium ring at the tail forward at a speed of 300 meters per second, colliding with the uranium ring at the head. The massive impact will also activate the neutron initiator, which will release a large number of neutrons. These neutrons will immediately bombard the uranium-235 atoms. As mentioned earlier, when a neutron strikes a uranium-235 nucleus, it will rapidly fission into two smaller nuclei, releasing energy in the form of heat, and also releasing 2 to 3 neutrons. And these 2 or 3 neutrons then collide with other atomic nuclei, causing new fission. This chain reaction will continue, and when it reaches a certain critical value, it will generates enormous energy. Eventually a mushroom cloud is produced. The Fat Man atomic bomb differs in structure from the Little Boy. It uses an implosion design. Now let's look at its detailed working principle. The Fat Man atomic bomb primarily uses plutonium-239 as the fission material. Like uranium-235, when plutonium-239 is bombarded with neutrons, it also splits into 2 smaller atoms, releasing 3 neutrons and a huge amount of energy. These neutrons then react with other plutonium-239, ultimately forming a fission chain reaction. However, the small sphere made of plutonium-239 is in a subcritical state. If we want the plutonium sphere to undergo a fission chain reaction and release massive energy, it must reach a critical state. The method is to compress the plutonium sphere. Under normal circumstances, the space between atoms is large, and the neutrons released by the fission reaction lose energy before they can react with other atoms, so the chain reaction cannot continue. But if we compress it, the gaps between atoms will be greatly reduced, allowing the chain reaction to be sustained. The problem is, Fatter, compressing it is extremely difficult, requiring at least 300,000 standard atmospheres of pressure, equivalent to the pressure exerted by 500,000 elephants. Not only that, the pressure applied must also be symmetrical to compress the sphere evenly. Obviously, we can't gather that many elephants, but we can replace the elephants with explosives. When the explosives are ignited simultaneously, the pressure from the explosion will press towards the sphere. However, the sphere gets compressed asymmetrically. To achieve symmetrical compression, we can place a circle of symmetrical explosives around the sphere. Each step, the explosives are composed of a combination of fast explosives, slow explosives, and fast explosives. In this way, when the explosives detonate, the shockwave converges inward, creating relatively uniform pressure, thereby compressing the object to the extreme. At this point, we can place some radioactive elements called polonium-210 near the object. Polonium-210 can release alpha radiation, which is absorbed by nearby beryllium, thereby releasing many neutrons. If these neutrons are directed at the core, a fission chain reaction will occur inside, releasing enormous energy. With this theoretical knowledge, let's now understand the construction of the Fat Man atomic bomb. The Fat Man atomic bomb is 3.3 meters long, 1.5 meters in diameter, and weighs about 4.6 tons. If you take apart the Fat Man, you will find that its internal design is quite complex, with layers upon layers. The innermost sphere, only 2 centimeters in size, is called the neutron initiator. The inner and outer layers of the neutron initiator are both polonium, and between the 2 layers is beryllium. As we mentioned earlier, polonium releases alpha radiation, causing the beryllium to release neutrons. Therefore, the main function of the neutron initiator is to emit neutrons. Wrapped around the neutron trigger is a 6.19 kilogram plutonium core with a diameter of only 9.2 centimeters. Outside the plutonium core is another concentric sphere made of uranium-238, whose main function is to serve as a neutron reflector. Return the neutrons that have escaped back to the core, thereby improving fission efficiency. Next, the outside of the uranium-238 sphere is wrapped with a layer of plastic shell made of boron, which can absorb escaping neutrons to prevent premature explosion. All these spheres are wrapped in a thick layer of aluminum material, which can evenly transmit the shockwave from the explosives to the central core. Next, the aluminum sphere is wrapped with 32 pieces of fast explosives composed of 60% composition B and 40% TNT. Outside the fast explosive, there is another layer of explosive, composed of fast and slow explosives. These explosives are also known as explosive lenses. To detonate these explosives, each piece is equipped with a detonator. Then, the entire sphere is encased in a thick steel shell, secured with bolts. Next to it is the X unit, which contains electronic components such as capacitors, responsible for generating a large current under high pressure and simultaneously distributing these currents through wires to all 32 detonators on the explosives. These are sensors, timers, and radar controllers. On the other side is the battery that powers the X unit and all sensors. All of these things are wrapped in a large casing. A radar altimeter is installed on the casing to measure the height from the ground. There is also a stabilizer at the tail of the casing to keep the atomic bomb relatively stable during its descent. After the Fat Man atomic bomb was completed on August 9, 1945, it was loaded onto a plane with the bombing target set for Kokura, Japan. However, the weather in Kokura that day was very poor, with heavy cloud cover. The pilot could not get a clear view, so the plane headed to the alternate target, which was Nagasaki. Fortunately, the weather in Nagasaki was very good, making it a suitable day for dropping a nuclear bomb. So under the pilot's operation, Fat Man eagerly jumped out of the cabin. When the radar altimeter detects that Fat Man is only meters from the ground, the ignition system will activate. The X unit on the side of the atomic bomb will discharge and send up to 5,000 volts of current to each detonator. In an instant, all the explosives will detonate simultaneously, generating a pressure wave exceeding 300,000 standard atmospheres. The immense pressure will pass through the aluminum sphere, plastic shell, and uranium sphere, ultimately reaching the core, causing it to reach a supercritical state. At the same time, this immense pressure will also cause the neutron initiator at the center of the core to break, which in turn causes the polonium and beryllium inside the initiator to mix. The beryllium absorbs the alpha particles emitted by the polonium, thereby releasing a large number of free neutrons. These neutrons then react with the plutonium atoms, causing them to fission into 2 smaller atoms and release 2 to 3 neutrons. These 2 to 3 neutrons will continue to strike other plutonium atoms, and like Little Boy, the chain reaction will keep going, ultimately producing enormous energy. A massive mushroom cloud was created, and Japan became the only country in the world to experience atomic bombs twice in succession. Actually, compared to the atomic bomb, there is a nuclear bomb more powerful than the atomic bomb, and that is the hydrogen bomb. Next, let's see how the hydrogen bomb is made. The hydrogen bomb is a fusion bomb which uses the nuclear fusion of hydrogen to produce energy. Hydrogen has only 1 proton and 1 electron, and it also has 2 isotopes, one with 1 proton and 1 neutron called deuterium, and another with 1 proton and 2 neutrons called tritium.
If you take
When deuterium and tritium fuse together, they become helium and release a neutron and a huge amount of energy, which is nuclear fusion. But there are two problems here. First, how to obtain deuterium and tritium. Second, how do deuterium and tritium fuse? Deuterium is easy to obtain. Seawater contains a large amount of deuterium, which can be extracted through distillation or centrifugation. However, compared to deuterium, obtaining tritium is very difficult as it is very scarce in nature. Scientists have discovered that by bombarding lithium deuteride with neutrons at high temperatures, deuterium and tritium can be obtained. Lithium deuteride is a stable white powder formed by the combination of deuterium and lithium, making it suitable for hydrogen bombs and fuel. With deuterium and tritium, how do they fuse to release energy? It is actually very difficult for the nuclei of two atoms to fuse. This is because there is a strong repulsive force between atomic nuclei. However, if we increase the temperature to several million degrees Celsius, the atoms will accelerate. However, to achieve nuclear fusion, the temperature must be raised to approximately 100 million degrees Celsius, while the temperature at the center of the Sun is only 20 million degrees Celsius. The immense temperature can greatly increase the speed of atoms, causing the electrons orbiting the nucleus to detach from it, allowing the nuclei to approach each other. When the distance between them reaches 10 to the power of -15 meters, nuclear fusion occurs. But how can such a high temperature be achieved? It's simple. The explosion of an atomic bomb can produce this temperature, so atomic bombs are usually used as the triggering device for hydrogen bombs. Now that we know the operating principle of hydrogen bombs, how are they made? Let's take the largest hydrogen bomb ever made by humans as an example. Let's explain using the Tsar Bomba. The Tsar Bomba is 8 meters long, with a diameter of 2.6 meters and weighs 27 tons. Let's take apart the hydrogen bomb to look at its internal structure. Nuclear bomb. The front half is a sphere, which is actually a fat man atomic bomb. As we mentioned earlier, the back half of the nuclear bomb is the hydrogen bomb part, mainly composed of 3 parts. The outermost is a cylinder made of cobalt. Next is the white nuclear fusion material, lithium deuteride. Inside is a plutonium rod. Then the entire inside of the hydrogen bomb is filled with polystyrene foam. Like atomic bombs, hydrogen bombs are also delivered by aircraft. During delivery, the entire aircraft is painted bright white to reduce the thermal radiation from the hydrogen bomb explosion. Accompanying the aircraft is an observation plane used to capture video footage and collect explosion data. When the Tsar Bomba is dropped, the parachute at the tail of the hydrogen bomb will open, thereby slowly reducing the bomb's descent speed, allowing the delivery aircraft enough time to safely leave the explosion point. The bomb is equipped with a pressure sensor to measure the altitude from the ground. When it is 4 kilometers from the ground, the atomic bomb inside the hydrogen bomb will first ignite. Sensors inside the atomic bomb will send a signal to release an electric spark from the detonator, which will rapidly detonate the shaped charge inside the atomic bomb. The explosion will produce a large amount of high-energy gamma rays and X-rays. The rays will cause the polystyrene foam inside the hydrogen bomb to convert into plasma. The high heat and pressure from the plasma compress the plutonium rod, exceeding the critical point. The lithium deuteride begins to react, producing tritium. Then, under the 100 million degree high temperature from nuclear fission, the atomic nuclei of deuterium and tritium undergo intense nuclear fusion, releasing enormous energy and producing helium, while also generating a neutron. The neutrons react with the outer layer of uranium and the plutonium at the center, triggering new nuclear fission. The new fission causes the lithium deuteride to produce more nuclear fusion. Fission and fusion interact, ultimately generating enormous energy in less than 1 second. The mushroom cloud can reach a height of 60 kilometers and can be seen from 1,000 kilometers away, destroying everything in its path.